Hello class. Today, Group 2 is going to be talking about the Hadoop distributed file system. So just an introduction to Hadoop. It was designed to run on commodity hardware. This is hardware accessible to the general public, so that means just cheap computers that you can buy at mass. Hadoop is a highly fault-tolerant file system. This is because every block is replicated when data is stored, and we'll get to that more in fault tolerance. It provides a high throughput of files, and this is because the files are divided into blocks, so random access becomes very easy and fast. And because of these two things, it is suitable for large data sets. It was originally built for the Apache Nooch web search engine. So, block and metadata design. Hadoop uses two nodes for the different operations of the file system, and those are name nodes and data nodes. Name nodes manage file system data, so that means like file names, file paths, permissions, etc. They control read and write operations, and so that's controlling who has access to read and write on what blocks. They keep track of nodes in a cluster, and a cluster is basically just a group of machines that store large files. The name nodes also signal replication, so they use that information that they get from the nodes in the clusters to signal replication whenever blocks are being created. And data nodes are slaves to the name node, so when name node signals replication, then data node will execute that replication. Same thing with the write operations. When a client wants to write, the name node will tell the data node what to write, and then the data node will write it onto a block. So the data nodes can write, but they can also create files. The data nodes also expose the data to clients when it's requested. And the organization of the file system, it's a master-slave architecture, so the data nodes answer to the name nodes. The name nodes are client level, so all of the client operations and functions will go through the name node to the data nodes. So data nodes answer to name nodes and are grouped together into racks. And usually there will be one data node for every node in a cluster. And then in those racks, the name node will assign operations, so write operations to a rack. So each data node will carry out the same operation. And we'll talk about how that works more in replication.
The HDFS allocates data for new jobs by making use of the MapReduce engine developed by Google. This is a derivative of the fact that the HDFS is an open source implementation of the proprietary Google file system, which was developed back in 2003. Around the time of 2004, the HDFS developers made use of white papers published by Google, which discussed the different algorithms they use to implement GFS. In specific, a job tracker program, as discussed by Google in their papers, is used by clients to submit MapReduce jobs. The job tracker program tries to find the nodes necessary to meet the resource needs of the specific job being submitted, and at first tries to assign the job to the specific node where the client resides. Should the node where the client resides not be available, it attempts to start the job somewhere on the same server rack as the client. And so from there, the HDFS tries to meet the ideology that jobs should be completed with the least network traffic possible. In specific, there are three main task scheduling techniques that are used by the HDFS. By default, HDFS makes use of FIFO, first in, first out scheduling. But with recent years, new task scheduling algorithms for the HDFS have been developed. In specific, we are going to discuss the two most commonly implemented. The most commonly implemented of the third-party algorithms is the fair scheduling algorithm developed by Facebook. The fair scheduling algorithm ensures fast response times for small jobs that use small amounts of resources and in specific are task critical, and with each of them having equal priority. From there, this is met by grouping jobs into pools, and each pool is guaranteed at least a portion of processing time in a round-robin sort of fashion. Once a group is freed, when the jobs inside the group are completed, the freed resources are then equally distributed to the already existing pools. And from there is no specific pool that gets more resources than the other when a job pool completes. This is in contrast to the capacity scheduling algorithm, which was developed by Yahoo. In this algorithm, queues are used to prioritize nodes and jobs in the system. From there, once the prioritized job completes, the resources dedicated to that job are then reallocated to the highest priority job in the queue. And this is because the jobs inside the queue require the resources in an immediate form rather than in the fair scheduling algorithm. The jobs in the pools can complete at any sort of time but are anticipated to complete at a sort of same time. Rather, in the capacity scheduling algorithm, the jobs submitted are expected to be completed in the order they are submitted. The downsides of the HDFS data allocation techniques that we've discussed include the fact that the job tracker process is a severe bottleneck towards the performance of the HDFS. Choice of a scheduling algorithm is a key for the swift allocation of resources so that jobs don't hold the required resources for too long. And in specific, should they hold those resources for too long, the system itself experiences severe inefficiencies. To solve these problems, various companies and individual contributors towards the HDFS project have created different scheduling algorithms to circumvent this problem that the FIFO model, alongside the job tracker process, create severe bottlenecks. And in specific, because HDFS is now seeing more recent use in Web 2.0 solutions such as search engines and social media websites, various implementations of HDFS exist that make use of these custom algorithms. However, the vanilla form of HDFS that you can download directly off the internet and make use of immediately does suffer from the fact that the FIFO model is just not as optimal for today's applications as it was in 2004. However, with small jobs, as the anticipation of you using HDFS, you are also using lower end hardware. If you're, as a result, using less strenuous jobs on the system, the FIFO model should perform fine. But at a corporate application level, such in the case of Facebook and Yahoo, the FIFO model for the sheer amount of jobs that are submitted is just not optimal anymore. And there is a limit to how many jobs you can truly use with the FIFO model with optimal results.
The next aspect of HDFS that we'll be exploring is fault tolerance. HDFS is a very fault-tolerant file system, and it's for good reason. So Hadoop was designed to run on commodity hardware, and this is just hardware that is accessible to the general public, and this means that not only can they find it, but they can purchase it. It's very low cost. And so Hadoop was highly fault tolerant and runs on low cost hardware easily. Since an HDFS can contain a multitude of server machines, now the thing is, not only does it contain a multitude, it also contains a multitude of low cost server machines, which means that it has a very high likelihood that there is a non functional component at any given time. So the chances that there is a fault somewhere in the system at any given time is very high, which means that HDFS needs to be able to deal with these in an effective and efficient and fast manner, and it needs to be able to correct and detect these errors quickly and efficiently. So next we're going to talk about fault tolerance protocols. So the protocols that HDFS uses to communicate. So Hadoop communicates using the TCP/IP suite. This suite is the basic protocol layers that every data communication software or system uses. And these layers include the application, transport, data link, network, and physical layers. These all have specific protocols of how they communicate with the other layers, specifically the layers that are directly above and directly below them. This keeps most data communications safe and non-corrupted. But not only does Hadoop use these protocols, it also uses three of its own protocols. It uses a client protocol, and this dictates how the client communicates with the name node. So the client can't just communicate with the name node any given way. There's a specific, you could say even language, to how they are meant to communicate to one another so that they're both on the same page and can detect any errors that happen in that communication. Then the name node talks to the data node, and the data node back to the name node, vice versa. This is spoken through the data node protocol. And we try and keep the client from speaking directly to the data node to avoid any corruption that the client could inflict on the data node, because the client doesn't understand how to speak to the data node as well as the name node does. So it's like it goes through a middleman. And then a remote procedure call wraps both of these protocols up with the TCP/IP suite and all of its protocols. So next we're going to be talking about the actual technique that Hadoop uses to tolerate faults. So we'll hit three different failure types and discuss how Hadoop actually notices that there was an error and fixes them. So first we're going to talk about a data disk failure, and this is when a whole data node either dies or gets corrupted. So throughout a data node's lifetime, it sends heartbeats to the name node periodically, like every second or so. Every so often, it sends a heartbeat, essentially like a pulse. So the name node can tell if the data node is still alive or not. If a data node stops sending these heartbeats, or the name node stops receiving them from the data node, then the name node can feel no pulse on the data node, which creates the notion that the data node is dead or corrupted or for some reason can no longer function. So the name node then ceases to send any IO requests to that data node anymore. Even if it's requested by the client, the name node no longer requests in or output to or from that data node. That data node is then replaced. So the way Hadoop works is that it keeps a replica of every single one of its data nodes at any given time. So there are at least two of each data node. There are two copies. If one dies, then using the other copy, the name node creates a second copy. So there will always be two copies of each data node, at least, in the entire lifespan of the file system. So when a data node stops sending heartbeats, the name node creates another data node and just increases the replication factor sometimes, but it's safer that way. Now, touching on a data integrity failure. So a data integrity failure is just when some specific data bits are flawed. So it doesn't have to be the entire disk, it can just be little pieces within the disk of just small data failures. So HDFS implements a checksum to check if the data is received correctly. So these checksums are stored in a separate and hidden file, but the way these checksums are calculated, so before the data node sends any data to the name node, it calculates this checksum from the data, and then when it sends the data, the name node can check that data against the same checksum to see if it has changed or not. And if it has changed, then it is obviously no longer the correct data. So if the checksum does have a discrepancy, the client will ask the name node to send an IO request to the other data node copy, which, as we heard before, there are always two at least. So it asks for the same data from the other replication of the data node instead. So lastly, we'll talk about a metadata disk failure. So this is similar to a data disk failure, except it's not data that the client is using specifically, it's data that HDFS is using to run the file system. So the central structures of this metadata for HDFS are the FS image and edit log. So edit log is kind of just like a transaction log of every single edit that is made on this file system. And these files are very important to HDFS. If either of these files are corrupted or if they don't exist anymore, then the HDFS instance is no longer viable. It just cannot run anymore. It just does not work. So in order to prevent this from happening, the name node updates multiple instances of these files as backups. So note that not only does the name node create multiple instances of these, it keeps them updated in the same way. That way, there are so many different ones that you can choose from. So if one fails, you have plenty more. So these are just backups, essentially. And then when the name node has to restart, so if the file system is shut down and then has to be brought back up, it simply chooses one of those up-to-date files, one of the up-to-date and uncorrupted files for startup. So this is how Hadoop tolerates faults. This is the process that it uses, the technique that it uses for detection and for correction. And fault tolerance is a very large aspect of the HDFS.
HDFS or Hadoop replication. Hadoop or HDFS replication enables you to replicate your HDFS data from one HDFS service to another, synchronizing the dataset on the destination service with the dataset on the source service. Based on the specified replication schedule, this makes the storing a large file faster. You can also replicate HDFS data to and from Amazon S3 or Microsoft ADLS. Cloudera Manager Server managed by destination services where the replication is being set up and the source service can be managed by the same server or by a pure Cloudera Manager server. You can also replicate HDFS data within a cluster by specifying different source and destination directories. In order to minimize the chances of data loss, the blocks are replicated on at least one off-rack machine. For this to happen, the file has to have a replica count of greater than 1. HDFS stores each file as a sequence of blocks. All blocks in a file except the last block are the same size. The block size and replication factor are configurable per file. An application can specify the number of replicas of a file. The replication factor can be specified as file creation time and can be changed later. The name node makes all decisions regarding replication of blocks. It periodically receives a heartbeat and block report from each of the data nodes in the cluster. Here's an example of an HDFS block replication. The way HDFS stores a file is that the file is broken down into multiple blocks. Then each block will be placed on the target computer or node cluster. If this happens because, for example, if there's 10 computers, then the chances of one of those computers to fail is pretty high, even coming from minor issues. For this example, we have 5 blocks coming from a file. The replica factor is 3, and there are 5 nodes in which the files will be stored in. As you can see, each block is replicated 3 times and is randomly put into different nodes. This would, if we take, for example, if node 1 were to fail, we will still have those blocks, copies of those blocks into other nodes. Based on the replica, there would be two more nodes that would be a copy of those block laws. Here, blocks 2, there's block 2, node 2, and block 2, node 4. For block 4, there's block 4 in node 3, and then block 4 in node 4. Block 5 is stored in block 2, and then node 2 and node 5. Consistency technique. Data consistency level determines how many nodes should confirm that they have stored a replica, so that the whole write operation is considered a success. HDFS used the master-slave consistency technique. The master, which can track the files, manage the file systems, and has the metadata and the whole data in it. To be particular, name node contains the details of the number of blocks, location at what data node and the data is stored, and where the replication are stored, and other details. Here we have an example of data consistency for HDFS. Here we have HDFS will write a file and create two replicas. In this case, the system will refer to node 5 first. Then node 5 will ask node 12 to store a replica, and finally, node 12 will ask node 20 to do the same. A write is considered successfully when all replicas have been successfully written. This guarantees data consistency. The data nodes also serve as blocks when clients request them to do so. They remain in touch with the name nodes, periodically send disk utilization reports, and periodically send blocks report. The blocks reports are used by the name nodes to map the blocks of a file to its location.